Welcome to a new video. In this video we will discuss the Gauss-Jordan elimination. The Gauss-Jordan elimination is a modification of the Gauss elimination, and it greatly simplifies the back substitution phase we have seen in the Gaussian elimination, the previous example. So when we calculate unknowns like x, y, z, we have directly the results using this method. Okay, let's see what we need to do for this example. Of course, we will again see the calculations for a specific matrix, which will be then eliminated in this form, really simple form. We will see that shortly, step by step, and also verify these in the MATLAB command window. Now let's look at our example. We'd like to solve the following system of equation using Gauss-Jordan elimination. And this is the system of equation. You see here 3 equations and also 3 unknowns, so x, y, and z. But this is a little bit disordered, so we need to first do the ordering. We will see that in the solutions now in the calculations part. First step is put this system of equations in the standard form. We also see that in the example of the Gaussian elimination. So what we want is we like to have the x, y, z is equal to a constant. This form we need to have also in the second and the third equation. So I need to look at the first equation. Do I need to change this? In this case, I need to replace this 2y to the left side, so it will be minus 2y. The x and the z are in place there, so that can be there, so stay there. But I also need to put that in the order like x, y, and z. The second equation is x, y, and there is some z in the right-hand side. Also, that needs to be placed to the left side, so I have here minus 4z. You see again that I have only a 3 and the 1 left, so that is our unknowns and the numbers, I must say. And we have here x minus 3z is equal to 5. Now that's exactly as this one, so the third equation was already in the nice format. Okay, that was our first step. The second step is put this system of equations in the standard form in the augmented matrix. That means put this in a matrix form and augment that using these solutions here, 3, 1, and 5, in this format. So you put a vertical line, which is an augmented version of the matrix, and you see here 3, 1, 5. You take the coefficients of each variable. So you see here 2, minus 2, 1, in a similar case 1, 1, and minus 4. So in order, x, y, z, and you see here a 1. There is no y here in the third equation, so that should be a 0, and then minus 3, and again the vector here as augmented form. What do we do next? Now we like to, again as we did in the previous example of the Gaussian elimination, we like to make this part, so this triangle, 0 first. That's still what we need to do here in the Gauss-Jordan elimination method. In addition, we will do then after that this part 0. And then the final part is make the diagonal elements, these all 1s. So we will see that now shortly in the steps. So first, in order to eliminate the 1 here, I need to multiply this second equation or second row by 2, so 2 times the row 2. And also multiply this third row by 2, so I have this first step. So I don't do anything with the first row, so I will take that completely. So I copy that first, so that is also my advice always. What is not changing, take that first. And this is changed, so double this, double this, double this, and double this. That's actually what you see here. You also need to double all these numbers here, so you get actually what you see here. Okay. Next thing is we did this in order to do the following operation, which is then the row 2 minus row 1, and then row 3 minus row 1. That's all shown here. So these are the 2 operations we need to do now next. Again, the row 1 stays the same, so that is unchanged, so we copy that right away. Now this minus that, so 2 minus 2 is 0, 2 minus minus 2 will be 4, minus 8 minus 1 will be minus 9, 2 minus 3 will be minus 1. So this is for the second row at the moment. For the third row, in a similar case, 2 minus 2, 0 minus 2, that's actually plus 2, and minus 6 minus 1 is minus 7, and 10 minus 3 is 7. This is now what we have. Now, the next step is in order to make this 0, I need to double this. So again, 2 times the R3. So again, we go to the next step and we get this. So now the row 1 and row 2 are not changing. You just copy them, and this is now just 0, 4, minus 14. This is plus 14. Now we can do the next step, which is then the row 3 minus the row 2. So I just copy this here, so I don't have space here. So this is exact same as the final form of the matrix. Now row 3 minus row 2, what you have is then this. What is not changing? Again, row 1 and row 2, because row 3 is only changing. So we copy the row 1 and row 2 right away, and then we get here 4 minus 4 is 0, minus 14, minus 9 will be minus 5, and 14 minus 1 will be plus 15. So this is now what we have. Now this is already the Gaussian elimination step, so we can also stop here like we did in the previous example, and then do the back substitution to calculate the x, y, and z. You can already see what the z should be here. So this is minus 5 times z is equal to 15, so z must be minus 3. But we will now do the Jordan method, so the Jordan part. Now is that part coming, so we can see that clearly in one picture. Okay, what do we do next? Now, in order to eliminate these 3 values and also change that to 0, we need to also change that such that the subtraction and the additions are easily done. So I can do the following. I can say let's multiply the row 1 by 5. Why? Because I have something with a 5 here, so that can be then operated really easily. So this is 5 times, and the rest stays the same. So I copy everything here, second row and third row. I just make this 5 times, 5 times, 5 times, 5 times. That's all here. Now I do the following step. I say row 1 plus row 3. Why? Because I want to make this 0. I also make this 0, of course, and also this 0. So step by step. Now that's the operation what we do now. Now again, this is not changing, this is not changing, so just copy that. And now we have here 10 plus 0, minus 10 plus 0, which is still minus 10. 5 plus minus 5 is 0, that is what we wanted, and 15 plus 15 is 30. What you see here is the following. Now we have a 0 here. You see now that we already have 1 0. Now, in order to get this also 0, I can look at this and this row, and this minus 9 and this minus 5, so we can see what the ratio is. So in order to calculate what the multiplication factor for this third row must be, we can say this is 9 over 5, which is 1.8. So I can then multiply this row 3 by 1.8. I have here also minus 9. Let's copy this first here, because there is no space there, and do this operation, which is then this 1.8 times R3, which is this. And then we only change the row 3, so row 1 and row 2 are not changed. So we can just copy them. The row 1 and row 2, and row 3 will be minus 9 here, and here 15 times 1.8 will be then 27. Okay, then now we can see here that the row 2 can be also here, this part of the row 2 can be also made 0 by doing row 2 minus row 3. Okay, that's what we do now. Again, row 1 is not changing, row 3 is not changing. That is the only change is row 2. So we have here 0 minus 0, which is 0, 4 minus 0, which is 4, minus 9 minus minus 9, which is actually a plus 9. So we get actually 0 here, and minus 1 minus 27 is minus 28. You can already see also what the y should be, because this is 4 times y is minus 28, but you get actually now closer to the nice expression or format we wanted to have for the Gauss-Jordan elimination. Now the final step is make this 0. So how can we make that 0? Now for this, in order to make this 0, we do not use the row 3 anymore. Why? Because if I use that, I get also another value which is not 0 here. So I can only operate that with row 2. So how do I do that? Now I look at this one, I can say, okay, this needs to be also set to 10. So that means I need to multiply this by 2.5. So I say, okay, multiply row 2 by 2.5, that's it. And then this other 2 rows stays the same. So just copy the row 1 and row 3 first. 0 times 2.5, 4 times 2.5, which is 10. 0 times 2.5, and minus 28 times 2.5 is exactly minus 70. Now we can say row, let's first copy that, by the way, because we don't have the space again here. So we can say in order to make this 0, I can now say row 1 plus row 2. So that's the next step. Now we get the following. Only row 1 is changing, so row 2 and row 3 we can copy. This is 10 plus 0 minus 10 plus 10 is 0. I mean 10 plus 0 is 10. Minus 10 plus 10 is 0. 0 plus 0 is 0. 30 plus minus 70 is minus 40. That's what you see here. So you can see already that we have also a triangle here with the zeros. The final step is make these diagonal values, elements, 1. So I need a 1 here and 1 there and 1 there. And the easiest way to do that is just divide this by 10, this by 10, and this by minus 9. This is actually the next step. So you see here row 1 by 10, row 2 by 10, and row 3 by minus 9. Then you get this one. So if I divide this by 10, will be minus 4, minus 7, and this will be minus 3. What you see is actually a pretty nice expression, or pretty nice augmented matrix in this final form. You see here it is 1 times x is equal to minus 4, 1 times y, which is minus 7, and 1 times z is minus 3. So in other words, the solutions are minus 4, minus 7, and minus 3 for x, y, and z. So this is indeed really easy to see. Of course, we can also do that in this step already by back substitution, but it will take also sometimes more time, and this is a nice way to see that clearly here. Let's now check that these values are indeed correct, the solutions. So we can do that by substituting these values in these equations. So x minus 4 will be then here, minus 7 here, and minus 3. That's actually for this equation should then sum up to 3 by evaluating this equation. Let's see that. 2 times minus 4 is minus 8. And you get here minus 2 times minus 7 will be plus 14. So in total you get here plus 6, minus 3, because plus minus is minus. So 6 minus 3 will be 3. So this is indeed correct. Now let's see also the second equation. Here we put a minus 4. Here you get a minus 7. So that's actually what you see here. And here you get here minus 4 times minus 3. So this should add up minus 4, minus 7 was minus 11, but this is minus 4 times minus 3 is plus 12. So add up to minus 11 plus 12 is plus 1. And here you get here minus 4, minus 3 times minus 3. This here is plus 9, minus 4 is exactly 5. So this is indeed correct. So we check that. So our solutions are indeed correct looking at these equations by substituting these values. Okay, now let's go to the MATLAB command window. This is how we define the matrix, what we have here. And this is how we define the vectors. And this is how we solve it. So we can see that indeed this is what we have here. So minus 4, minus 7, and minus 3. So this is indeed correct. So from this matrix, you see here 2, minus 2, 1. This is the after the standard form. You see that also here 2, minus 2, 1, 1, 1, minus 4, 1, 0, minus 3. And this vector here, which is the augmented part of the matrix, is given here as b. And then you do now this operation, which is lin solve, and then a comma b in the parentheses, and you get the v as the vector of the solutions, which is then in order x, y, and z. So that means we also have verified this in MATLAB. Alright, that was our example considering the Gauss-Jordan elimination for this 3x3 system of equations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.